All right, so in chapter 21, we're going to be looking at nuclear chemistry, and then this is going to involve a different type of reaction. Because up to this point, when we're looking at chemical reactions, when we're looking at chemical changes, we were essentially just taking the atoms we had and then breaking bonds, reforming new ones. So we kind of just had the electrons kind of moving around to give us those new substances. So to this point, we could think of the reactions as something like this. So A plus B, just giving us compound AB. So we still have the same atoms, we still conserve mass. But now with the nuclear reactions, and there's going to be different types. We're going to see nuclear decay, fusion, fission. What we're going to see in this case is we could take atoms A and B, and we're actually going to be altering the nuclei of those atoms in order to give us a new element. So in this case, A plus B just gives us element C. And like I said, there's going to be different forms of these types of reactions. So fusion, fission, radioactive decay are all going to be different in terms of exactly how those processes take place. But they're all going to have the same similarity of we're going to be starting the reaction with one set of elements. It may just be even a single element, but we're going to be starting with something and then just having it convert to a new element entirely. Whereas the chemical reactions, we had those same atoms, we just rearranged them differently. And then with the nuclear reactions, we also have, we're going to show it in terms of the way we write through the reactions as a conservation of mass. But with the nuclear reactions, if you think about nuclear weapons, so atomic bombs or nuclear power plants, those are going to have a tremendous amount of energy involved with them. And the reason a nuclear power plant, excuse me, can turn just a small amount of fuel into a tremendous amount of energy is because we've got the relationship between mass and energy. E is equal to mc squared. So if we lose a little bit of mass in these nuclear reactions, that mass is going to be related to energy by taking the amount of mass and multiplying it by the speed of light squared. And the speed of light is going to be 3 times 10 to the 8th meter per second. So if we take that number and square it, no matter what the mass is, even if it's a very small amount, it's going to be equal to a large amount of energy. So with the nuclear chemistry, with nuclear reactions, just think about we're making new elements, and there's going to be a tremendous amount of energy involved with these processes, much more energy than the chemical reactions. And then in terms of sort of how nuclear energy works, we'll later on in the chapter, we'll kind of see how those power plants operate. But you can just see here, and then this graph is a few years old at this point, so the actual values may be slightly different, but they're not going to be tremendously different. But we can see worldwide, nuclear power makes about 1/8 of the energy sort of grid. So you've got hydroelectric, and then a whole bunch of fossil fuels mixed in there, solar, wind, geothermal, going to be some of the green energies. But then with France, we can see is going to be heavily reliant on nuclear energy. So about 3/4 of their energy is derived from nuclear reactions, whereas the United States, just a little bit above what we see worldwide. So about 1/5 of the energy we have in this country comes from nuclear power plants. And then China, kind of the opposite end of the spectrum, relies greatly on those fossil fuels. So we can see coal is just going to be about 80% of it. And then the nuclear power plants are just going to be a small fraction of that. And then when we talk about the power plants themselves, we'll also mention the safety and things like that. But you're probably familiar with like Chernobyl and things. So if you've ever seen the HBO TV series on it, that's a dramatization of it. So it's not completely factual. But of course, there was devastating disasters related to power plant malfunctions in Chernobyl, so part of the Ukraine. Japan had the power plant that was affected by the tsunami. So we'll talk about those issues as well. But typically, nuclear power plants are going to be actually safer and expose people to less radiation than even coal burning power plants would. But with these reactions, like I mentioned, we're going to have a change in the nuclei of these different atoms. So we're going to be creating new elements, and then depending on if it's decay, if it's fusion, fission, we'll see differences in kind of how that process occurs. But because we're going to have changes in these nuclei, and because there's going to be different forms of these atoms that are going to be important. So when we think about a chemical reaction, for instance, if we have a combustion reaction, we kind of just write like CO2 as the product. Doesn't matter to us if it's carbon 12 or carbon 13. We just have carbon in there, because either way they're going to react the same. But with the nuclear reactions, we're going to see that the specific isotope is going to be important. So when we write out these nuclear equations, we're typically going to write them out in this form, where not only do we have the symbol, but we're also going to have the atomic number and the mass number included there, because certain isotopes are going to be radioactive, meaning they'll have these reactions occur, other ones won't. And in that case, it's going to be important that we actually specify which isotope we have. So just with this notation, remember the top number is going to represent the mass, so protons plus neutrons, just basically how many particles do we have in that nucleus, whereas the atomic number on the bottom is just going to be those protons. And technically, we could exclude the 6 here and still have the same information, because just by having the symbol for carbon, we know it's got to have 6 protons. Otherwise, it would just be some other element. But typically, we'll include both of these numbers just so that it makes it easier as to kind of examine those different equations. And like I mentioned, these isotopes are going to be different. So if we just think about uranium, uranium-235, going to be the version that's actually used in nuclear weapons and things, but there's going to be other isotopes here. So if we had uranium-238 versus 235, those nuclear reactions are going to look different. And that's why we've actually got to specify which of these isotopes we have. And then related to that, there's going to be certain isotopes that are going to be stable. There's going to be other ones that are going to be unstable, and that's going to be referred to as radioactive, those unstable ones. And sometimes those are referred to as radionuclides, just because the nucleus itself is going to be the thing that's essentially causing that radioactivity. And in other cases, they're just known as radioisotopes as well. But with it, we'll look at a few different ways that these radioactive atoms can essentially sort of break down. We're going to refer to that as radioactive decay. And then depending on the exact process that occurs, there's going to be different versions of that decay. And then we'll look at each of those kind of individually. But with this, we'll see beta decay and positron emission are going to be very similar. It's just going to be kind of referring to if it's a positive or a negative piece that's being ejected from the nucleus. Gamma emission is going to be related to releasing energy. And then electron capture is just going to be taking on an electron. But if we look at these ones, 1 through 4, again, 2 and 3 you can kind of count as the same, because it's just going to be kind of positive or negative is the only difference there. But as we go from alpha to beta to gamma, what we're going to see is the penetrating ability of that radioactive decay is going to increase. So alpha decay is going to be the least penetrating. Gamma emission is going to be the most penetrating. So with alpha decay, substances that undergo that type of radioactive decay, if we just had that sample kind of in the lab with us, it actually wouldn't really cause too much damage, because the alpha decay, those alpha particles we're going to see are just helium nuclei, wouldn't actually be able to penetrate the body. But now if we ingest something that's going to undergo alpha decay, then that substance is in our body. It's going to release the alpha particles within our body. And at that point, it's going to be able to damage the cells and cause a whole bunch of issues. Whereas the beta decay and the gamma emission, those are going to be higher, have higher penetrating ability to begin with. So those may be able to penetrate the body, may be able to cause damage, even if we're just sort of around that substance. We don't necessarily need to ingest it like we would with the alpha decay. But with each of these reactions, again, we're going to have same sort of idea with reactants on the left, products on the right. But now we've got the mass and the atomic number included with these. And we just want to make sure that we have that balance. So with the alpha decay, again, just going to be a helium nucleus. So 2 protons, 2 neutrons. And with this, it'd really be +2 overall. But it's going to be good at gaining electrons from other things, so we can kind of just consider it to be the whole helium atom. Just because it's going to be, as it sort of is ejected from the uranium in this case, it's going to be good at just gaining other electrons. But in this case, we can see alpha decay. We're going to see whatever that radioactive substance is initially. Since it's emitting a helium nucleus, the mass is going to go down by 4. The atomic number is going to decrease by 2. So in this case, we're going to be taking uranium and converting it into thorium. And then we just have the helium as the other piece there. So again, this is going to be the alpha particle, and that's why we refer to it as alpha decay. So with these type of nuclear reactions, a common question is kind of show the entire reaction with just one missing piece. So if we were missing the thorium here, we could identify what that product's going to be by just looking to see what the mass is on the left, how much do we already have for mass on the right, and then just identifying that 234 in this case would be that missing piece. And then the same thing with the atomic number. We had 92 on the left. We already have 2 from the helium from that alpha particle on the right. So that missing piece would just have to be 90. And then we could check our periodic table, see what element is atomic number 90. And we'll see that in this case, it's just going to be that thorium. And then the other types of decay are going to be similar. It's just going to be kind of dependent on what this piece is, will affect exactly what type of decay it is. And then with the electron capture, we'll actually see we'll have a second reactant. So we'll have an electron be that reactant there. But with the beta decay, this is essentially just going to be kind of ejecting a electron from that nucleus. But if we look at the reaction at the bottom, on both sides, the masses balance out to 131. On both sides, the atomic number balances out to 53. So in this case, what we can kind of think of it as is on the left, oops. On the left, we'll have 53 protons. So we'll do 53 P plus, and then we'll have 78 neutrons. So then on the product side, if we look at the xenon, now we've got 54 protons and 77 neutrons. So we still have the same number of particles overall. It's just with the beta decay, we essentially convert one of these neutrons into a proton. So that's why we see neutrons go from 78 to 77, protons go up from 53 to 54. And then with the neutron itself, it's neutral overall. So if we're converting that into a positive, that means we need to be ejecting a negative piece. And that's what we just see with the beta decay. So we're releasing a beta particle, which you can basically just think of as a high energy electron, because we're ejecting that from a neutron. And then because we're ejecting the negative charge without changing the mass, that's just going to convert it to a proton, basically. So with the beta decay, we'll see the mass number for that substance is going to stay the same, so 131 to 131. But the number of protons is going to increase by 1. So that's why we go from iodine to xenon in this case. So with the beta decay, we'll always take whatever that radioactive substance is and have it move to the next element, one higher up in terms of its atomic number, because it's going to be converting one of those neutrons into a proton. Okay. And then with the positron emission, going to be a very similar idea. It's just in this case, the positron itself is just going to be a positively charged particle. So rather than taking a neutron and converting it into a proton, we're just basically going to have the reverse occurring. We're going to take one of these protons, convert it into a neutron, and that's why we go from 6 protons to 5. So that's why it's carbon to boron. But then the mass number stays the same because the number of subatomic particles in that nucleus is still going to be 11. But because we're converting from a positive to a neutral piece, we're just ejecting a positive charge from that nucleus. And that's why we see the positron being emitted here. But again, and you can kind of base it on the name itself. So electron is a negative particle. A positron still has that same ending, but now positive sound, or positron sounds like positive, so it's just going to be a positive electron, basically. So it still has no mass, but it's just going to have the opposite charge, so +1 rather than -1. But again, with the reaction, if you look at the left versus the right, we have 11 on the top of both sides, we have 6 on the bottom. So if we're missing one of these pieces, we could still identify what we need those numbers to be. And then we could identify either what the product's going to be or the reactant, or if we're missing the final piece here, that's how we can identify what type of decay it's going to be. So in this case, since we have a positive one, we could identify it as a positron emission. If we had a negative one on this piece, then it would just be this previous one, it would be that beta decay. If we had 4 and 2, then that helium nucleus is just representing the alpha decay. And then the next one, gamma emission. So you'll see here, doesn't have a mass, doesn't have a charge. That's why this is just going to be a ray. It's just going to be high energy radiation. So a gamma ray is what's going to be emitted during gamma emission. Typically, we'll have some other particle with it. So in this case, we also have that beta particle. But with the gamma emission, we're just going to be releasing that high energy radiation from the nucleus. But because we also do have the beta decay in this case, that's why we can see 27 to 28. So cobalt becomes nickel, and then nothing changes about the mass here because both the beta particle and the gamma ray are going to be massless. And then just with the final one, electron capture. Some of these names kind of tell us exactly what's going on there. So with the positron emission, positron is, again, basically just a positive electron, and then emission just meaning to kind of get rid of it, to shoot it out of the nucleus. So with the electron capture, now we're just thinking about the nucleus again, because we're focused on nuclear chemistry. So the reactions involving these nuclei. So with electron capture, we're just going to see the nucleon itself, or the nucleus itself rather, is going to capture an electron. And because of that, what we're going to see is a proton is basically just going to get converted into a neutron. But with this one, just note that the electron, since it's being captured by the nucleus, is now being considered a reactant, whereas beta decay, it was ejecting that electron, ejecting that negative particle. So that's why we had it as a product here. So with the electron capture, what we're going to see is the mass stays the same, because the electron is massless, at least so negligible that we ignore it. There is a small amount of mass. But now we've got a positive charge, a negative charge, and that's why we just wind up with a neutral neutron overall. So in the case of electron capture, we'll see the mass is going to stay the same, but then the atomic number is going to be decreasing by 1. Whereas with the beta decay, the atomic number increased by 1 because we were losing that negative charge from the nucleus. So we were converting one of those neutrons into a proton. So with the next couple of slides, it'll kind of just be practicing writing out some of these types of nuclear equations. So in some cases, we'll have the radionuclide that we're starting with. We'll know the decay type, so we can figure out what that product's going to be. In other cases, we'll be missing one of the other pieces. But for all of them, we just want to think about writing out the chemical, or not the chemical equation, the nuclear equation. So to see the first one here, radium-226, the way we would want to approach this undergoes alpha decay. So we want to write that entire nuclear equation. We want to figure out what that product's going to be. So with radium, we can find it on the periodic table. Ra is going to have an atomic number of 88. And then this is going to be one of the substances that Marie Curie actually did a bunch of work with. Her and her husband won Nobel Prize for their work on radioactive substances. And then radium was used in a whole bunch of different things before they realized how harmful it was. But you may have heard of the radium girls, because radium is going to be kind of glows in the dark. So it was used on the hands of watches for like the minute and the hour hands. But with the radium girls, they were painting the watches with this radium paint. And then their paintbrushes, as they would paint, would kind of lose the fine tip. So then in order to get it back they would take the paintbrush that contained this radioactive paint and place it in their mouth in order to get the tip back to that fine point. And then because of that, they were exposing themselves to radiation, ultimately led to a whole bunch of horrific health effects with it. Which is unfortunate because otherwise alpha decay, the radium wouldn't really be too problematic if you're not ingesting it. But since they were placing the paintbrushes into their mouth, of course, that was occurring, and it led to a whole bunch of different issues. But we want to figure out what this product's going to be. And because it tells us it's going to be alpha decay, that means that we're going to have a helium nucleus. So when we're trying to figure out what the product's going to be, we just have to look to see what those other numbers. So at 226, the right side still has to add up to 226 for the mass, but we've already got a 4 from that alpha particle. So we're going to have 222 for the mass, and then kind of the same idea with the atomic number. It's just in this case, 88 on the left. We already have 2 on the right, so that missing piece just has to be 86. And we're going to see that radium, when it undergoes alpha decay, is going to give us radon, Rn. And we'll talk about radon later on as well, because that's going to be another radioactive substance. I forget if it's particular this isotope, but we'll see radon as well. So with the next one, if you want to kind of practice on your own, just pause the video so you can kind of do the same thing. But in this case, we want to figure out, instead of what the product of lead-208 undergoing alpha decay is, in this case, we know we're going to produce lead-208 via alpha decay. So in this case, we know the right-hand side, PB, and then the mass is going to be 208, PB, whoops, sorry, it's just hard for me to do it with this mouse. PB, since it's lead, it's always going to have 82 protons. So with the mass part, we need that to be given to us in the equation, or it has to be the one that we're solving for. Otherwise, there's just too much ambiguity to know for certain. But then again, we have alpha decay. So we're going to have a alpha particle. We're going to have that helium nuclei. So when we're looking at the product, we just need to add up both of these lines. So with the mass, we'll wind up with a mass of 212. We'll wind up with an atomic number of 84, which is going to be another element that Marie Curie worked with. It's going to be polonium. So we're taking polonium-212, having it undergo alpha decay, so losing that alpha particle, resulting in lead-208. And again, just double check, make sure the numbers on top balance out on both sides. The numbers on the bottom do the same. And we've got 212 and 84 on both sides. So that'll just be our equation for the alpha decay of polonium-212. Because again, remember this number here, 208, in the case of lead, represents the mass. Because with lead itself, we know the atomic number, but with the lead-208, now it tells us exactly which isotope of that element we're going to have. Okay, and then we've got 2 more to look at on this slide, and then there'll be 1 more, I believe, on the next one. But it's going to be that same idea. It's just in this case, we're looking at different types of decay. So for the first one, mercury-201, we don't even need to look at what type of decay it is at first, but we know if that's what we're starting with, we can write the symbol. So mercury-201 means we'll have a mass of 201, and mercury means we'll have an atomic number of 80, symbol of Hg. And then it tells us it's undergoing electron capture. So this is actually going to be the case where we've got another reactant. Electron capture means we're going to have a mass of 0 there, and then an atomic number of -1. So to predict the product, we've just got to do the same thing. So add up the masses. Electron capture is not going to change the mass at all, so we still have 201 on the right. But in this case, we've got that -1. So we're going to see the atomic number is going to change. It's going to decrease from that original substance because now it's taking on that negative charge. So 80 becomes 79, which is going to have the symbol AU just for gold. So if you've ever heard of alchemy, kind of the precursor to chemistry, had some weird stuff going on, kind of like a magical version of chemistry. Was one of the focus of it was turning different substances, transmuting them into gold. So this could kind of be a version of alchemy because we're taking mercury and then ultimately producing gold from it by having that mercury nucleus gain one of these electrons and convert one of those protons just into a neutron. And again, since we're converting a proton into a neutron, the mass stays the same, but the atomic number just decreases by 1. And then for the second one, in this case, we know the product, we know the reactant, but we've got to figure out what type of nuclear decay it's going to be. So for thorium-231, thorium going to be TH, 231 just being the mass. And then it's got an atomic number of 90. And again, we can just get that from the periodic table, just look up thorium. But the mass has to come from the question. And then we're having that get decaying into protactinium, which has the symbol Pa, and then it tells us mass of 231 as well. And it's got an atomic number of 91. So in this case, we need the numbers for that missing piece to be 0, just because we already have mass of 231 on both sides. And then for the atomic number portion, we need it to be -1, because on the left we only have 90, but on the right we already have more than that. We already have 91, so we need something to subtract from it. So what we're going to see in this case is this would just be an example of beta decay. Oops. So with it, you could put the beta symbol like I have there. You could put E for electron, but in either way, we're going to see that the nucleus is basically converting a neutron into a proton. That's why we see the protons increase by 1, and then it's essentially just ejecting a high energy electron from that nucleus. But again, on both of these equations, we can see the mass is going to be equal on the left versus the right, and then the atomic numbers do the same thing. So we can always check just to make sure we've got that balance with both of those values. And then with the final one, write a balanced nuclear equation for the reaction in which oxygen undergoes positron emission. Oxygen 15 undergoes positron emission. So we can do kind of the same thing. Oxygen with a mass of 15. And then since it's oxygen, atomic number always going to be 8. So it tells us positron emission. That positron is just going to be basically a positive electron. So we'll have 0 on top, 1 on the bottom. So when we look at the product of this one, the mass isn't going to change. The mass will still just be 15. But now the atomic number for that product of the decay is going to be 1 less because we're emitting 1 from the particle. So we've already got 1 of the 8 we need here. So we're just going to wind up with 7. So we're going to see oxygen 15, if it undergoes positron emission, is going to decay into just an atom of nitrogen 15. And again, double check, we got the same amount of mass on both sides, 15 and 15. We got the same atomic number on both sides, 8, and then 7 plus 1 giving us 8 on the other right. So we have that balance. And those are just a few examples, but if we know all of the pieces but one, we can either solve for what that starting radioactive substance is. We can solve for what the final product's going to be of that decay, and we'll see later on in certain cases we're going to see even that product may then undergo decay, so we're going to see kind of a chain reaction. Or we could figure out, if we have both of those pieces, we could figure out what the missing one is going to be. We can identify what type of nuclear decay it's going to be. But for the first video, that'll just be where we wrap it up for now.